This conference will now be recorded.
Hello everyone. We will start with chemical properties of alkynes, and that we are actually continuing already from the last class. Under polymerization type of reaction, one polymerization type which is linear polymerization that we have completed, and now we will start with cyclic polymerization. So as the name suggests, there will be some ring structure formation, and once we finish, then we will discuss some questions that is related to these reactions of alkynes and also CC double bond. So cyclic polymerization. So cyclic polymerization, there will be formation of ring type of structure, and on passing through red hot iron tube, when we are passing ethane through red hot iron tube, so that is the only reagent we are using here. Look at the temperature, this is very, very high. It undergoes cyclic trimerization, leading to the formation of benzene. So it is trimerization because total 3 molecules are coupled together and we are getting a benzene structure. So that is why it is cyclic polymerization. And you can also say that this is a very good method for the preparation of benzene ring, which will be our next topic. That is, once we are finished with the topics of alkynes, next we will proceed to aromatic hydrocarbon, where the simplest one is benzene ring, and then you will see, we will learn about benzene. So here you can already see how we can synthesize benzene ring starting from alkyne. Now this is the best route for entering when you are entering from aliphatic molecules to aromatic compounds. So this is a very good method. In presence of nickel cyanide, NiCN2, this compound, when we use as catalyst, and there will be high pressure, then it is also possible that total 4 molecules of ethane. In the previous one you have seen total 3 molecules, but total 4 molecules under high pressure, when we are using nickel cyanide as catalyst, combine to form tetramer, and that tetramer is cyclooctatetraene. So this is also a cyclic type of structure. As you can see here, total 4 molecules of alkynes, that is basically acetylene, or you can say ethane. So total 4 molecules in presence of high pressure and NiCN2, we are getting this type of 8-membered ring. Right? This is, previous one is 6-membered. We are using total 3 molecules of ethane, but now it is total 4 molecules of ethane. And the structure is cyclooctatetraene, which is 8-member ring. This is cyclic polymerization. Now the final reaction type, which is isomerization. So this is E. So we have already covered A, B, C, D, E. A, B, C, D, that means we have seen addition reaction. Under addition heading, there we have seen different types of addition. There is oxidation, there is just we have seen polymerization. Now we will discuss isomerization. So isomerization means from one isomer there will be formation of another type of isomerization, isomer formation, and that is why the name is like this. The equilibrium in linear alkynes has been shown to heavily favor the internal isomer. So if you have any alkyne which is terminal, suppose we have RCH2 triple bond CH. So this is terminal because here we have carbon hydrogen bond. The carbon which is triply bonded with this H is attached. So that is why this is having terminal hydrogen. Heavily favor the internal isomer. That means if you consider the corresponding internal isomer. So now what will happen? This triple bond, that is CC triple bond, both sides there will be some R groups. And how that is possible? That is possible if I am shifting this triple bond to right hand side, to left hand side, and now there will be CH3. So see, total number of carbon hydrogen I have not changed. I have just shifted the position of the triple bond. The initial structure is there is presence of carbon hydrogen, that is the terminal CH, but here we do not have any terminal hydrogen. That is the difference. This carbon is as if now shifted. So the first structure is terminal, that is one alkyne. Why it is one alkyne? Because this is position 1. So it can be isomerized to thermodynamically more stable. The second one is thermodynamically more stable. And this is 2-alkyne because now the name will be 1 and then 2. The position of triple bond is now from position 2. And what kind of base we can use? See, look at the base. These are strong bases. It is not normal NaOH cable. These are strong bases. Sodium hydride. Then we are using potassium salt of, that is, you can also the tertiary butoxide. Potassium tertiary butoxide, that is the full name. But if you remove this K plus, the remaining structure is tertiary butyl O. Tertiary butyl means what? This group, total 3 methyl group attached to carbon, and then there is O minus. So this is the structure of OBUT. So this is a very strong base, and it can capture this H, and detailed mechanism we are not discussing here, but in presence of this type of strong bases, obviously as we are using bases, so this hydrogen will be captured by these bases, and there will be formation of C minus, and then there is some mechanism. We are not going into that, but remember, in presence of this type of bases, we can get internal alkyne. If we want to do isomerization in the opposite direction, that means now you want to move from internal alkyne to terminal alkyne. How you can do so? You can do so with strong bases such as sodium amide at high temperature. Now we are using another strong base, which is sodium amide, and you have to do this at high temperature, and which are able to completely deprotonate terminal alkyne. So this type of base, that is sodium amide, that is when you are moving from internal to terminal alkyne, can be accomplished with strong bases such as sodium amide, and also we have to use a very high temperature. Then only it is possible. Okay. Uses of alkynes. Acetylene is used in oxyacetylene torch, which is used for welding and cutting metals. For welding and cutting metals, high temperatures are required, and in presence of oxygen and acetylene, the combination of these two can produce very high temperature. Okay, so that is the reason. Acetylene used in the manufacture of ethyl alcohol, that is C2H5OH. Then CH3CHO, which is acetaldehyde, acetic acid, CH3COH. Then there is various types of polymers also. The names are mentioned here because under chemical properties we have already seen the polymerization reaction. So you know how the polymers are generated starting from CC triple bond, right? Acetylene used as mild portable lamp, which has been called acetylene gasoline lamp, hooked up in homes, bicycles, vehicles. So these are very common application. Thin film of polyacetylene can be used in electric wiring, electrode material, in lightweight rechargeable batteries, and commonly used to artificially ripening of fruit. Acetylene and its derivatives are widely used in synthetic organic chemistry for synthesis of Cs and transalkene. So starting from CC triple bond, we can produce this double bond C, but that is also in two manner. That is, it can be Cs or it can be trans. Now that depends on what type of reagents you are using. Okay. Then we can also get methyl ketone. So all these conversions basically we have already studied under the heading of chemical properties. Because chemical properties of alkyne, that is very versatile. There is addition, there is oxidation, there is polymerization. Everything we have discussed. Okay. So you can now understand all the applications. So that is not just application as for, that is in some lamp or ripening fruit. These are one type of application. Then there is another application is that starting from alkyne, you can make some other important compounds. That is another type of application. So both types of applications we have seen here, right? Now we will move to some questions. CH3C triple bond MgBr can be prepared by the reaction of which of this combination? Okay. Now, whenever you are seeing this term MgBr, one thing is clear that we have to use Grignard reagent. There is no doubt about it. Only from Grignard reagent we can get this type of unit MgBr. Now, when Grignard reagent we are talking about, obviously there has to be some terminal hydrogen, that is the active hydrogen. So if you have any alkyne, like in general if I write CH, So because of the presence of this active hydrogen, now if you are using any Grignard reagent, suppose you are using R prime MgBr. So Grignard reagent, there is carbon metal bond, that is carbon Mg bond. So this R prime, that is the negative part, so this will be acting as base and it will capture this H. Now if this part is acting like a negative charge over R group, or maybe methyl, ethyl, whatever, it is capturing this H. So what will happen? Now you will get RC triple bond C. So negative charge is here. Now this is the positive part of Grignard reagent. So now it will come here and you will get some alkane because R prime, which is nothing but some alkyl group, now it is attached to H. So this is alkane. But this type of product is actually given in the question, isn't it? Where R group is CH3, that is the only difference. So that means if you want to prepare RC triple bond CMgBr, where R group specifically is methyl, what starting material you have to, if you move backward, what you need? You need CH3C triple bond CH, that must be used as starting material, right? Now, this is present, not present in option E, so you can cancel it. But this is present here, option C, option D. But what is the other reagent? That also you have to consider, right? So it is not MgBr2, it has to be something like R prime MgBr. So it is not MgBr2, it is not KBr Mg metal, but this is CH3 MgBr, where the CH3 part is acting as if it is CH3 minus, though I will not say that there is free CH3 minus ion generation, but it will act something like this type of species. So this will take this H and here you will get CH3C triple bond CMgBr. Okay, and that is given in the question. So this should be our correct answer, the last one. We'll go to the next question. Which of the following reactions give or is, that means it may be one reaction, it may be more than one reaction. But what it will give? It will give meso compound as the main product. Now meso compound means what? There is internal plane of symmetry, or you can call sigma plane. Internal plane of symmetry is theta. Now look at the reactions one by one. The number one reaction is a trans compound is given, right? This is alkene trans, and you are using the reagent bromine in DCM, dichloromethane. Now this type of addition, remember in the under the chemical properties of alkene, there we have seen when we do bromine addition to alkene, this is basically anti-addition. Now the compound is already in trans fashion and you are doing some anti-addition. So this type of thing I have already discussed before. Again, I am saying this because we are solving up this problem. So if you are having any doubt, just go back to that section where the chemical properties of alkenes are used. That is the bromine addition to CC double bond. There it is clearly mentioned it is anti-addition, and when it is trans compound as a substrate you have taken, so it is already trans, that is something anti, and your addition is also anti. So if you remember it in this way, it will be helpful for you to remember that whether when trans compound is given, whether you will get meso compound or you will get some chiral compound. So if you try to remember in this way, so it is trans, it is already anti, and the mechanism is also anti. So as if anti and anti, right? So ultimately what will happen? You will get some meso compound. So detailed mechanism, how we are getting meso compound, I am not going into details, that will be repetition. So that is already in detail discussed, the in chemical properties of alkene. Just check that part. So it will, it should give us meso. Now the next reaction is hydrogen in presence of PDC, that is palladium and carbon. Now this addition is basically syn addition, that is both the hydrogens, as the hydrogen here we are using PD carbon, that is palladium is on the carbon surface. So here the addition of hydrogen to CC double bond, that is actually taking place on metal surface. So on the metal surface these hydrogens are there, And when CC double bond, that is alkene, is approaching to the metal surface, both the hydrogens are added from the same side. If hydrogens are added from the same side, that means suppose it is adding from the front side, that is on towards us. So it will be like this. Now these two methyl groups, they are already in the same site. These two ethyl groups, they are already in the same site. And now the two hydrogens are also added from the same site. So the compound that will be generated, obviously, it will be a meso compound. There will be internal plane of symmetry. That is why it is meso compound, because the addition is seen. Suppose if the given compound is given in this way, that is ethyl group is here, another ethyl group here. Now see, both the methyl groups are opposite. Under this condition, if you are using this reaction H2PDC, obviously it will not be meso. But it is already given in Cs and the addition is seen. So that is why both the hydrogens that will be added from the same side, and ultimately we will get meso compound. Okay. Next is hydrogen and linear catalyst. Now linear catalyst is such a catalyst where the CC double bond that is converted to CC double bond, and both sides we have methyl groups, ethyl groups, and hydrogens that are added from the same side, because linear catalyst that also occurs on the surface of metal where both the hydrogens will be added from the same side. And once this CC double bond is formed, further reaction is not possible. That it is not that further another H2 molecule will be added and you will get some alkane. No, it is not like that, because linear catalysis is such where from triple bond, CC triple bond, you can get CC double bond only, not some, you can proceed further. Now the question of meso does not arise here, because it is already having some CC double bond, and meso compound, this terminology we cannot use here. Then so this should not be considered as correct option. Then we have again CC double bond, and bromine will be added in anti manner. Now the compound is, it is cyclic structure, so it is obviously both the groups will be towards same side. So as if it is equivalent to some cis alkene, isn't it? Suppose if you have some open structure, not ring structure like that. So one open, that is equivalent structure, I can write something like this. These sides are now open. So here you, as if this is also cis. Now cis, and but addition is anti. So what will happen? The addition will be one bromine if up, another bromine will be down. Or the opposite possibility is this one. But this is not meso compound, because if you draw a line here, it is not internal plane of symmetry. Both halves are not mirror image to each other. So it is not meso compound. Okay. So these two will not lead to meso compound. So ultimately what we'll get, that is from which reaction we can get meso compound, it will be the first two reactions. Okay. And both these reactions details how we are getting meso compound, that you can get in the corresponding section where we have discussed chemical properties of alkenes. Total number of alkyl bromides, including stereoisomers, formed in the reaction. So here Me3CH double bond CH2, this is a substrate. So substrate is basically alkene, and this is HBr addition. Okay, so we know when we consider HBr addition to alkene, and if the alkene is unsymmetrical, here the alkene given is unsymmetrical, isn't it? So you have to consider Markovnik of addition. Now no peroxide is there, so peroxide effect you don't have to consider, nothing is mentioned. And it is asking total number of alkyl bromides. That means the product will be alkyl bromide, because when you add H and Br to CC double bond, you are adding HBr, any substituents. So what we get? We get alkyl halide, or you can say alkyl bromide. So whether how many possibilities are product possibilities are there, including stereoisomers, that we have to find here. That is the question it is asking. Now, if we write this molecule Me3C CH double bond CH2, the first step is addition of H plus. Now when we are considering addition of H plus, and if it is Markovnikov addition, then this is the carbon number 1, which is containing lesser number of hydrogen. So in that carbon, bromine should be attached. So that should be the final product. But here we will not directly write the final product. First we will write the carbocation, because there is a chance of rearrangement. And because of this rearrangement, the product possibilities will increase. Okay. So just whenever you are getting this type of question, just check by writing stepwise mechanism. Don't write the final product directly following Markovnikov, because if you do so, you will not get the correct answer. So what you have to do, write stepwise mechanism. So when first H plus is added, the possibility is that H plus will be added to carbon number 2 according to Markovnikov. Because if you are doing so, you are getting positive charge here, which is secondary carbocation. But if you are doing the another addition, suppose I am using different color, if it is not according to Markovnikov, then this will be positive charge is here and H is added here. But this is 1 degree carbocation, which is not stable at all. Now whether you will consider this as product, because next if you add Br minus, you get the product Me3C, CH2, CH2Br. And here stereoisomerism not possible because you do not have any chiral center. Now if you consider this 2 degree carbocation, which is the more stable carbocation, so you have to give more preference. Here if you add the bromide ion, it will be generating this type of product. Now just check whether there is any chiral center or not. Yes, there is chiral center. This is the chiral center, isn't it? Because with carbon 4 different groups are added, H, Me3C, Br and methyl. So it will be having one more isomer, enantiomer. If it is R, another one will be S or vice versa. So from this you will get total 2 products. But you also have to check whether any rearrangement is possible or not. Yes, here it is possible. Suppose if this methyl I am writing separately, this can be shifted here. And when this is shifted, positive charge will be now on this carbon. Now this is more stable. Why? I know that this is 2 degree, this is more stable than this one. But if you consider this carbocation, it is in 3 degree. Now it is even more stable. Suppose this is carbocation A, carbocation B, carbocation C. C is more stable than B, then A. Now from this carbocation, if you add Br minus, finally you will get Me2C Br, CHMe2. Now there is no chiral center. So if you have to consider this also as product. So this is one. Here we have already have 2 because of this chiral center. So 1 plus 2, 3. And if you consider this one, though this is very minor, actually this one is minor, this will be major. But if you do not follow Markovnikov, then this is very, very minor. But as it is mentioned, it is asking that total number of possible alkyl alkenes. Suppose if you are considering it will be answer will be 4. But 4 is not given in the options. So you just have to omit this one. Suppose in some cases the option may contain 4. So in that case you can choose it, because there is a little chance of formation of this product. But still, just check that if the options there is no mention of 4. So maximum probable answer you have to choose option C. So here we are not considering this one. We are only considering carbocation B and carbocation C. From B carbocation, the product generated is chiral. So that is why stereoisomerism possible. And from C, there is only one product. So total 3. This is the correct option. Here we have another question. So here it is mentioned, that is the substrate that is given. It contains CC double bond as well as it contains, this is the CC, triple bond, and it also contains CC double bond. Both sides there is 2 different types of reagent. In the left hand side it is mentioned sodium in liquid ammonia, solvent is ethanol, and this is generating product C. In the right hand side there is mention of H2 Ni2B catalyst. Now this is something I have not discussed before, but remember it is called nickel boride complex. So when you add hydrogen to a CC triple bond in presence of nickel boride complex, which is also called P2 catalyst, what happens? This is also metal surface reaction. So hydrogens are added from the same side. So it will be seen addition. Just like you have seen any hydrogen addition in presence of metal catalyst. So this is also like that. And in presence of nickel boride catalyst, it will be only reaction to the triple bond. The reaction is not to the double bond. You can find some similarity with linear catalyst. Okay, there also we have seen that it reacts with triple bond, there is generation of double bond, and then there is no further reaction. So it is also just like that. So you are getting product B. Now which statement is correct about the above reaction? First option is saying that both are optically active. Second option is saying that both are inactive. C is saying B active, B inactive, C active. And product B is formed by anti-addition. Product C is formed by syn addition of H2. Right? C is syn addition, but actually C is will be anti-addition. So this is not correct statement. Because we know when we add sodium in liquid ammonia, this is anti-addition. So the left hand side mechanism is anti-addition, but the right hand side mechanism is syn addition. But that is fine. We now know that option D is not correct. That is fine, which is not true for this above reaction. But how we will get some optically active, why the question of optical activity arises? See, when this CC triple bond is converted to double bond, this center will be chiral center. How? First I will write this reaction. So when this reaction is happening, both the hydrogens will be added from the same side. Now, this center will be chiral center. Because, or you can also write it, even if you write it in this way, that is, suppose I am writing both hydrogens are added from this side, methyl H. Now in whatever way you write, actually doesn't matter, you will always see that this is syn addition, this is also syn addition. So this center, I'm talking about this center, is it chiral? Actually it is not chiral center, because 4 groups must be different, but here these 2 groups different, that is fine, but this side and this side, or you can consider the second structure also. This is also, that is, if you consider this part, it is basically a cis orientation. This is also cis. So both side you have some cis CC double bond R group. So both side as if it is equivalent to writing as if both side you have same group. I'm writing G here so that you can understand. Similar groups are there. So this center will not be optically active. That means B must be optically inactive. B must be optically inactive. But we also have to check whether C is optically inactive or not. Now this is anti-addition. When we are talking about C, it is anti-addition, isn't it? And when it is anti-addition, now what will happen? H double bond R methyl. See, these 2 hydrogens are added anti-fashion. And this side as it is, because double bond is not attacked. So this side, now you are getting trans, this is cis. So as if this is equivalent to, if it is G prime, this is G. So these 2 groups are not same. So this will be optically active. So this is your C and this is your B. B is optically inactive. This is optically active. That means option C should be the correct option. One of the product, when it is trans addition or anti-addition, it is that is the left hand side product, C is optically active, because now both side of this carbon center you have G and G prime. G prime is trans and G is cis. So that is the reason we have to choose option C and other options are not correct. So in this question, sorry for my handwriting, but probably it is understandable what is written. M is written. Okay, so when M is treated with hydrogen and Lindlar catalyst, you are getting product N. When N is undergoing ozonolysis reaction, there is formation of O and P. We know ozonolysis means what? When there is CC double bond, you get two different carbonyl compound from both sides, right? So that is why O and P. Now among O and P, when O is treated with CH3C, this is basically AC2O, that is the structure if I write. This is sodium acetate, that is sodium salt of acetic acid, and this is sometimes it is also written as AC2O and ACOH. Both are actually same thing. So it is CH3CO, O, then okay. So AC, in short, it is called AC2. Now O and P in that is only O is undergoing this reaction, and it is mentioned here as cinnamic acid. Now what is cinnamic acid? Cinnamic acid is this structure. Actually, to solve this question, you should have some prior knowledge, and this reaction is known as Parkin reaction. This is a name reaction, though this is not it is not for this chapter. It is not related to particular to this chapter, and you can consider this question as if it is combination of 2 units. So some carbonyl compounds, that is there is a chapter oxygen related compounds, that is carbon, ketone, aldehyde, acid. So in that chapter, Parkin reaction is relevant, not here. But to solve this question, we have to know what is Parkin reaction. Now here we have another information which is mentioned as ammoniacal silver nitrate. Now this reaction we have already done. Ammoniacal silver nitrate. When you add this reagent to some terminal alkyne, we know there is formation of white precipitate because the terminal hydrogen that is kept, that is this H is replaced by Ag. And also instead of using AgNO3, if we use Cu2Cl2, that is cuprous chloride, then also there is formation of red precipitate, but precipitate generation is there. Now this type of white precipitate generation is only possible if it is terminal. Okay, so terminal alkyne, sorry, here one mistake I have done. This oxygen will not be there. CH3CO whole 2, it is 1 CH3CO, 2 CH3CO, and in between there is one oxygen. This is the actual structure of acetic anhydride or AC2. Now what I am saying that this must be terminal. That M means it must be terminal alkyne. Now terminal alkyne, if we are sure about this, that means which of this option can be correct? These two are terminal. That means you can cancel these two because with option B and D, actually both are same. By mistake I have written same. There will be some difference. Maybe one of this pH it will be CH3. But these two are internal. It is not terminal. So that is the reason white precipitate generation is not possible. Now you are stuck between option A and option C. But in option C you have methyl group. So see, now O is from O we are getting cinnamic acid where pH is present. That means pH must be present in the initial structure of M. So if pH is present, if you know the structure of cinnamic acid, and if cinnamic acid is generated from O, and if we know Parkin reaction, basically Parkin reaction, what happens? You have benzaldehyde, and in presence of this AC2O and ACOH, there is formation of cinnamic acid. That means this part is coming from PHCHO. So this O must be the compound benzaldehyde, PHCHO. So this pH part must be coming from N, because in ozonolysis what we use? O3 and some reducing agent, zinc water. So this pH must be coming from N. And N, if it is containing pH group, that is benzene ring, then it must be coming from M, because in H2 and linear catalyst you are not using any pH related compound. So if M is containing pH and if it is also terminal because of this observation of white precipitate, then option A must be the correct option. So this much information is enough. Even you don't have to write the full reaction, and in this way you can also save your time. But this cinnamic acid structure must be known, otherwise it is difficult to write the structure. Now finally we will write the full equation, what is actually happening here. So in presence, if it is PHC triple bond C, in presence of this ammoniacal AgNO3, there is formation of PHC triple bond CAg, which is basically responsible for white precipitate. Now, if you are treating it with H2 and linear catalyst, this will be syn addition, and both the hydrogens will be added from the same side, and there will be generation of PHCH double bond CH2. So this is our N, this is our M. Now N is undergoing ozonolysis, and there is zinc water reducing agent, because this whole reagent combination is actually the ozonolysis. You cannot simply use O3. So from this side you will get PHCHO, and from the other side you will get formaldehyde. Now this is O and this is N. Now when O, you are treating it with Ac2O in presence of acetic acid, sodium salt of acetic acid, NaOAc or ACONa, then you will get cinnamic acid. Okay, so this is the full reaction, all the reactions if we write. But as I have mentioned, just try to answer in a even, that is, as much as possible, try to save the time. That is our purpose, right? So whenever you will see ammoniacal AgNO3, you are providing and there is generation of YPPT, it must be terminal alkyne. And cinnamic acid, pH group is there, so there must be some pH. So that is why option C we are cancelling. Option A should be the correct option. Okay. So this question has C11C. So this is alkene question. We are treating it with HBr. Now we have to apply Markovnikov, right? Now if you simply apply Markovnikov without writing the stepwise mechanism, which I always suggest, you will end up with the product like this. You will think that this carbon is containing lesser number of hydrogen. That means Br must be attached here and hydrogen must be attached here. And if you are choosing this as option, then correct option will be option B, isn't it? Second option, because the other two options are not possible. Here, as if CF3 group itself is not present, but CF bond cleavage is not possible. So these two you can easily cancel. But if you simply blindly follow the Markovnikov rule, which Markovnikov rule is obviously to assist us, but it is not that blindly you will follow. You have to understand the mechanism. What is the chemistry behind it? And if you want to know that, you have to write the stepwise mechanism. So when you write stepwise mechanism, see, the first step is addition of H plus, which is the actual electrophile here. So if you are adding the electrophile to carbon number 1, then positive charge will be generated in carbon number 2. This is carbon number 1, this is carbon number 2. Or another possibility is F3 CF3, you are adding hydrogen here. That means, same thing I have done. Okay, positive charge is here and you have added hydrogen to carbon number 2. Now among these two, forget about Markovnikov. Just try to understand which one is more stable. Obviously, this one is more stable. Sorry, the first one is more stable. This one is more stable because here we have this electron withdrawing group, which will further this structure, basically electron withdrawing group, which will further destabilize this positive charge. It is not CH3 group, it is CF3, isn't it? So 3 fluorine atoms are there, so it is highly electron withdrawing. It will destabilize this carbocation. So though the second one is according to Markovnikov, but still we will not consider it. And that is the reason this is also not the correct option. So ultimately, when finally Br is added, this is actually option A. Okay. So this is the reason why I always suggest don't follow Markovnikov blindly, just try to understand the mechanism. Because if you are simply following Markovnikov, you are reaching some answer, it will be very straightforward question and hardly you will get any straightforward question in exam, right? It will be always with some, there will be some twisting. Okay. The starting substrate is, there is presence of CC triple bond and there is also CC double bond. The reagent, there is 3 reagent combination, total 3 arrows are there. But first look at the first reagent. It is using sodium amide in presence of liquid ammonia. And there is also iodide containing compound. Now, whenever you are using this type of base, and this is terminal alkyne, so this hydrogen must be removed by this base NH2-. So there will be negative charge generation over this carbon. And this negative charge, it can attack here. And iodine is very good leaving group. So CC bond formation, this C and this C will be connected and I will be removed. Okay. Now don't think it is sodium in presence of liquid ammonia. So there will be trans addition. No, that is sodium metal in liquid ammonia, but it is NaNH2 in liquid ammonia. It is base. Its role here is base. And acidic hydrogen is present because it is terminal alkyne. Now, once this CC bond is formed, you will get this, that is this type of CC bond bond will be formed, right? Next reagent we are using H2 in presence of palladium barium sulfate. Now, when you are using this reaction, this will be triple bond because triple bond is not effective. It is still there. In presence of H2PD-BSO4, it is the reaction on the metal surface. So both the hydrogen are added from the same site. Seen addition, and also the reaction will be stopped at alkene position. Further reaction is not possible. CC double bond, the reaction will be stopped. Now until this position, we know what is happening. If it is X, this is X. If it is Y, this is Y. Next, we are using some reagent which we have not seen before. But this type of reagent is actually in detail discussed in the alcohol chapter, where you have some CC double bond. And when you add this type of reagent combination, that is BH3THF complex, this is number 1 step. And in the second step, there is hydrogen peroxide in presence of basic medium. So what happens? Here, net addition of water occurs. But net addition of water occurs in anti-Markovnikov fashion. That means the H and OH, these two unit, we know this is a negative. So this negative part will be added to that carbon which is containing higher number of hydrogen because it is anti-Markovnikov group. So that is why, suppose this side you have R group and H and this side you have 2H. OH will be attached to this carbon and H will be attached to this carbon. So finally what you will get? You will get RCH2, CH2, OH. So this is the reaction that happens in presence of this reagent combination. But and this is a very good method for formation of alcohol where you need anti-Markovnikov addition. So that is why this is not I have discussed in this chapter. This is from another unit. But that knowledge we require to answer this question. So now in this compound, you have total 3 different CC double bond. Total 3 different CC double bond. And when you are using this reagent combination, basically you will get OH group and H group addition. Now, if you look at the left hand side and right hand side ring, this is unsymmetrical, isn't it? Here you have hydrogen, here you have methyl. That means if it is anti-Markovnikov, OH will be added to this carbon because it is containing more hydrogen. And similarly, here also it is same type of group. OH will be added to this carbon and H will be added to this carbon. So that is why C, this is the addition. And if you consider this one, this is actually symmetrical. Both sides are same. So it doesn't matter which side you put OH. But this should be the structure of the final compound. Now look at the options. Option A is not possible because here 2H group added to CC double bond. This is absolutely not possible. Even if this part is also wrong because OH is added to death carbon where methyl is there. But just looking at this middle portion, you can cancel it. Then what is the problem with option B? In option B also, this portion is okay, but OH will not be added to this carbon. It should be added to these carbons only. That is why this is wrong. D is also wrong because two H groups are added, but this is not such a reagent where two H groups are added. It is basically when you use this reagent, it is net addition of H and OH as if it is hydration reaction because it is net addition of total one water molecule. This is also not correct. Only one option is left, which is option C, where you can find similarity with the structure that we have just written, right? So option C is the correct option. So first there will be removal of terminal active hydrogen, carbon ion generation. It will attack the carbon which is containing good living group I. So CC, this is the newly generated CC bond, and then H2PTBSO4, which is a reagent for conversion of triple bond to double bond only, not further addition. And this is syn addition. Now in the molecule Y, there is total 3 double bonds present. For the middle double bond, it is symmetrical. The question of Markovnikov does not arise, but it is net addition of H and OH. And for the 2 ring, the CC double bond is unsymmetrical, so you have to consider anti-Markovnikov. And accordingly, following all this, we are reaching the result, which is option C. So now, as we have discussed all the questions, we still have some time, so we can have some primary idea about aromatic hydrocarbons, or it is also called Arenes. So until now we have seen alkenes, alkane, alkynes, but now it is something, this is obviously hydrocarbon because our chapter is hydrocarbon, so there will be discussion of hydrocarbon compounds only, but it is having a special unique nature is there, which is its aromatic nature. Now what is aromatic nature in detail we have to see separately, but right now we will just try to understand what is its structure. So it is called arenes or aromatic hydrocarbon, and this, why we use this term aromatic, because originally, that is the origin if we consider some arene compounds, there is some specific pleasant smell they give, and that is the reason we use this term aromatic, because the term aroma means what, a very good smell, and from that we are getting the word aromatic. So if a compound is giving a good smell, so that is why we're calling it aromatic. But nowadays the actual modern concept is the term aromatic, it is no longer this is the reason that it gives pleasant smell. It now implies a particular type of delocalized bonding. So delocalized bonding means the double bond electrons, that is the pi electrons, they will shift their positions, they will change their positions, and that is the delocalization. And when there is the term we are using aromatic, there is also delocalization of electrons. So it is a special type of delocalization. So that is the term aromatic, or the property itself is called aromaticity. Now benzene is the simplest aromatic hydrocarbon. Remember when we talk about alkene, we say that the simplest one is alkene. When we talk about alkane, we say simplest one is methane. When we talk about alkynes, we say the simplest, that is the first member is CH triple bond CH, that is acetylene or ethane. Similarly, when we talk about aromatic compounds, benzene is the simplest aromatic hydrocarbon. And the next simplest is C6H5CH3. So this is benzene. There is 3 CC double bonds, and all these are carbon, and there is presence of total 6 hydrogens. So that is why the formula C6H6. And the simplest next member, what you can do? You can replace one H with CH3. So now this H will be converted to CH3. And the formula is now changed to C6H5CH3. Because now it is one H is replaced by CH3. So it is now H5 and one methyl group. And the common name we use for this compound is toluene. Now remember this C6H5 unit, it is also written as pH group. So you can write this molecule as PHCH3. This is also toluene. So C6H6, which is benzene, and so benzene, how you can write it? You can write it as PHH. Okay. So these compounds are circularly structured organic compound that contain sigma bonds along with delocalized pi electrons. Now why we are calling it delocalized? Because these double bonds, their positions are not fixed. They can exchange their positions. So suppose I am numbering this as 1, 2, 3, 4, 5, 6. Now when they exchange their positions, the new structure that I am drawing now, keeping the carbon number same. Now just compare with the previous structure. In the previous structure, you have bond between 1, 6, 2, 3 and 4, 5. But now it is between 1, 2, 3, 4 and 5, 6. So it has changed its position when you keep the carbon number same. So this type of delocalization of electrons is happening within the ring structure. And this is the reason that this type of compounds are very stable. But details of aromaticity, how we can determine whether a molecule is aromatic or not, that will be discussed separately, not now. So aromatic hydrocarbons are unsaturated hydrocarbon. It is obviously unsaturated because you have CC double bonds. And what is the difference in normal alkene? In alkene, the double bond, their positions are fixed. But in this case, you can see one CC double bond, it is conjugated with another double bond. So that is why delocalization is possible, which have one or more planar 6-carbon rings, and this ring is called benzene ring, to which hydrogen atoms are attached. Now with this ring, if I am adding another ring, that is also possible. So as if these two hydrogens, these 4 hydrogens are still there, these 2 hydrogens, that position I have had another ring, and this ring also there is a CC double bonds conjugated. So in these 2 rings simultaneously, all these 5 double bonds, they can undergo delocalization with each other because their positions are conjugated. It is not that these double bonds, suppose one double bond, if another double bond I am writing in this way, then in between these two, you cannot say it is conjugated because in between these two there is a sp3 hydrogen. When you put this double bond in the position that conjugation is possible, then only you can say that yes, this double bond can be, because when this double bond is placed here, this double bond has to move to the next position. Okay. Benzene ring is highly unsaturated, as you can understand, and in most of the reactions of aromatic compounds, this unsaturation of benzene ring is retained. So when you have reaction in benzene ring, what happens? These hydrogens are basically replaced by some other group. That means these CC double bonds are still intact. Okay. But when you have some alkene structure, suppose you have RH, then what type of reaction we expect? Addition reaction where this pi bond is broken, sigma bond is still there. But that type of addition you cannot expect here because this delocalization is giving this type of compound a stability. And a molecule will never try to lose its stability. The general nature of any molecule, they always try to be stable. So as there is some aromaticity, and because of that there is some stability gain happening by this molecule. So it will not undergo addition reaction. Yes, addition reaction possible, but only under drastic conditions. So what type of reaction you will expect? As if this H is substituted by some other group. Or in place of H, if you have other group, that group is replaced by some other group. So it is not addition reaction, it is substitution reaction. One group is exchanged by another group. So this is the very unique difference with other unsaturated compound, other unsaturated hydrocarbon, that is CC double bond or triple bond. But in benzene ring also you have triple bond, but still it has very major difference with double bond or triple bond. You cannot have same type of property, you cannot expect. Okay. So these are some that is a benzene ring, and this molecule where two rings are attached together, fused together. So this is the fusion point. It is called naphthalene. Then you can also have three rings together like this. This is anthracene. And sometimes this instead of writing these three bonds as there is delocalized, you also write it. Put a ring, that is, put a circle inside. So for anthracene or naphthalene, you can write the structure like this. So what is the meaning of this circle? The circle, it means that complete full delocalization is present, and that is why the structure is like this. Fine. So here it is highly unsaturated, and that is also clear from the ratio. Look at the ratio of carbon and hydrogen. It is 1:1, but this ratio we have not seen before. In case of this one, there is only in case of AC triple bond CH, you can say yes, it is 1:1. But further members, when you move the hydrogen number compared to carbon, it is not 1:1, but here it is 1:1 if you consider simply benzene ring. Now sometimes there is some aromatic hydrocarbon possible where this aromatic benzene ring will not be present, but still it will be aromatic, but and that they are called non-benzenoid, but we will not go into the details for those, that we'll discuss in the next class. So today we will finish here just with the introduction of what is aromatic hydrocarbon or arenes. So remember here the basic structure that must be present, and for this level, that is for our syllabus, simply we will start with benzene and benzene related compounds because it is very vast chemistry if you consider aromatic hydrocarbon arenes, but we will just have initial idea. So our discussion will be mainly focused on benzene ring and benzene derivatives because there is also anthracene structure, naphthalene structure, but that will not be the part of discussion. Here I have mentioned this compound just for example so that you can understand the variety of aromatic ring. So this is anthracene. When two rings together, it is naphthalene. Naphthalene, you know, we all use it at home. So for our level, that is syllabus, we will just focus on benzene and benzene related compounds. So next day we will see what is non-benzenoid compounds. That is, in spite of not having benzene structure, some compounds can be aromatic. And why they are aromatic, to understand that in detail, we have to know the criteria. For when those criteria are fulfilled, then only you can call a molecule, yes, it is aromatic. That will be discussed separately. And we'll see some structural features of benzene in the next class. Okay. So today we are ending the session here. Thank you for listening.